Today I'm going to talk about carrier concentration. Let's start. To calculate carrier concentration, we should first know about the density of state. It is a very important concept in this lesson. Density of state in one dimension, if the length of this in here, x equals 0 to x equal L, we can draw a energy EK diagram like this. And in one dimension, we can know about the psi equal A is JKX, and in one dimension, we already know about psi 0 equal psi L, so we utilize this equation to calculate the density of state in one dimension. In one dimension, we can, if we substitute the x equal L in kx so we can note KL equal E pi n. So it also means Kn is E pi n over L. So we can use this equation. After complex calculation, we can know about the density of state equals SEDE, and yes, we calculate like this. And in conclusion, we should know the density of states is inversely proportional of energy, the square of energy. Then let's look about two dimensions. Two dimensions psi equation is this, and yes, it's equal kx and ky is 2 pi nx over lx like this. Then in two dimensions, the energies have discrete energy levels. So in graph, there are very discrete energy on the graph, and it looks like point, and if we look upper side in that graph, it looks like circle. So circle like this. So we should know about the area of this red. So use kinetic energy equation or like this, so we can calculate the density of state equal like this. However, this equation is not the function of energy, just constant in two dimensions. In three dimensions, it's same, kx, ky, kz. Then we use the volume equation in this dimension. So after complex calculation, the density of state means like this. So I draw the all graphs at those dimensions. Three dimension looks like this, graph looks like this, and two dimension, one dimension, and zero dimension. Zero dimension means the quantum dot, so it has only one energy, density of energy. Yes. Then let's talk about Fermi-Dirac distribution. Fermi-Dirac distribution can calculate like this based on this equation. Before we talk about Fermi-Dirac distribution, we should know about the energy band gap. This is conduction band and this is valence band. The middle of those bands, we call this line is mid gap. And after if we dope in conduction band, the metallic level is go higher than mid gap. So we should know the difference of Fermi-Dirac level. This is Fermi-Dirac level, electron and hole. We can calculate the Fermi-Dirac level based on this, and this is about hole equation. And in this chapter, our goal is calculate the carrier concentration. Carrier concentration is equal to density of state and Fermi-Dirac level concentration distribution. So we study about density of state and Fermi-Dirac level. So this is electron and this is hole. So electron equal density of state and Fermi-Dirac level. And hole equal density of state and 1 minus Fermi-Dirac level. At 3D dimension bulk, we can calculate the number of electron and number of hole. So NC, we can calculate the number in this equation, and in this equation, NC means the effective density of state in conduction band, and NV means effective density of state in valence band. Lastly, let's talk about extrinsic semiconductor. Extrinsic semiconductor is not intrinsic semiconductor. This is after we talked in semiconductors. So this number of electron equal the number of electron in intrinsic semiconductor plus donors. This ND means donors. This is N-type. However, Ni, the number of electrons in intrinsic semiconductor equal 10 to 10 squares. However, donors equal 10 to 18 squares. So donor is very, very bigger than intrinsic. So in engineering approximation, we equal ND equal N0. So the number of donors equal the number of electrons in N-type. It is also same in hole. So today we talk about carrier concentration. Thank you for watching my video. Bye.